So the next speaker is Brent Westbrook from the University of Mississippi, and he will be talking about reparameterization of models in MOPAC for polycyclic aromatic hydrocarbons.
Okay, can you see my screen and hear me?
Yes. Yep.
Okay,
good.
Awesome. Okay, yeah, so like Jonathan said, I'll be talking about reparameterizing PM6 for PAHs. And first of all, I wanted to give a few slides of motivation. So in the group I did my PhD in, we were mostly focused on astrochemistry. So what I'm showing here is just an example of the unidentified infrared bands, or UIRs, which are observed around all kinds of astronomical objects. This is just one example from Orion Bar. And going back to the 1970s, these have been hypothesized to be carried by small mineral grains, such as the one you can see here. But these didn't really match up with all the characteristics of the UIRs as they're observed. So this hypothesis was amended to include, small molecules on the surface of dust grains, such as this. But this still didn't really match up with the UIRs themselves. So what characteristics are we looking for in these infrared frequencies, or in the molecules that cause these infrared modes? Well, the first one is that they have to emit in the mid-IR, even when they absorb a single UV photon. So this is what kind of ruled out those large dust grains. So those molecules would be too large to have the right heat capacity for this. They also need to be stable. So these are, again, observed throughout space, throughout the universe, I guess. So they're expected to be stable so that we can find them. And then, of course, the carriers have to actually have bands that match existing data. So this led to what's called the PAH hypothesis for polycyclic aromatic hydrocarbons. So the current idea is that molecules such as the ones shown here, naphthalene, ovalene, circumcoronene, are the ones carrying the UIRs. And so this is what starts to get us towards MOPAC, because there's still a lingering question of which PAHs are causing this. And there are a few problems with the kinds of calculations that my group conventionally did. So we usually compute anharmonic vibrational frequencies of molecules and use coupled cluster theory for that. So most of our methods have been constrained to very small molecules, like 4 or 5 atoms, and not very symmetrical molecules. So we knew right away that we wouldn't be able to just go out and compute the vibrational spectra of PAHs using those conventional techniques. So to combat that, there are some existing solutions, such as the NASA Ames PAH IR spectral database, and it has a bunch of DFT data, like we've talked about quite a bit today. But it uses a very small basis set, and even then, it's restricted to molecules of about 400 atoms. When in reality, we would like to compute the spectra of molecules going up to maybe 1,000 or more atoms. And the other issue with the PAH database is that most of the vibrational frequencies therein are computed using scaled harmonic frequencies. So what we're trying to do is compute explicit anharmonic frequencies, as we do for our small molecules, but we need to be able to apply this technique to larger molecules like PAHs, and that leads us to choose faster methods, such as the semi-empirical methods in MOPAC. So to do these calculations of infrared frequencies, we use quartic force fields. These are 4th order Taylor series expansions of the potential energy surface that you can see here. And our conventional methodology involved first optimizing the geometry of the molecule, and then basically mapping out the grid of the potential energy surface by displacing that equilibrium geometry. At each of those geometries, we compute the single point energy, and then we transform those energies either by using finite difference or some kind of fitting technique to force constants from whence we can get frequencies. Now, the way we did that in the past is that we would optimize and compute single point energies with some kind of quantum chemistry code, in this case, MOPAC. And then we would basically string together several Python and Bash scripts, and at the end, 3 different Fortran programs to convert between coordinate systems, generate our potential energy surface, and finally actually get spectroscopic data. So something that's been closely tied to my work on MOPAC is automating that whole process in this piece of code that was recently published in JCTC called pbqff. So this stands for push button Cortic force fields, and it's all open source. It currently allows you to run automatic Cortic force fields in symmetry internal coordinates, Cartesian coordinates, or normal coordinates. And importantly for today, it includes an interface to both MOPAC and MolPro. It also interfaces to some queuing systems like Slurm and PBS. And this is really handy because many of these potential energy surfaces require thousands, or for PAHs, even sometimes millions of single point energies. So instead of running these all serially through a single quantum chemistry code, pbqff allows you to distribute these computations across a whole cluster using these queuing systems. And then at the end, it also has a VPT2 implementation that actually spits out vibrational frequencies. This is just another look at pbqff and kind of the ecosystem of independent packages involved. So here in the middle, we've got Enter, which handles the coordinate transformations. ANPASS handles our potential energy surface fitting. And one of the big ones, Spectra, is the VPT2 implementation. So in all these cases, pbqff depends on these separate programs as libraries, but they can also be used as standalone executables. And pbqff is actually the same way. On the executable side, this is what input looks like. It has a very simple TOML style input. So you basically just put in your geometry. And there's also a graphical interface here on the right. And this is, the ideal is to be close to WebMO. Basically, you paste in your geometry, you select from some predefined templates, and then at the end, you can click run. Now, to take a quick look at the output, the main output, especially for the context of this talk, are the vibrational frequencies. So you'll see that out come the harmonic vibrational frequencies, as well as the anharmonic vibrational frequencies, where the anharmonicities are derived from the Cortic force field I showed before. You also get things like the equilibrium and the vibrationally averaged and vibrationally excited principal rotational constants, as well as the quartic and sextic centrifugal distortion constants. Now, to move into the second part of my talk, you may have noticed that the accuracy of these frequencies may not look quite right. So using just the default PM6 parameters, you don't get the best anharmonic vibrational frequencies compared to experiment, or whatever I'm calling best here. And if we compare this to the scaled harmonic frequencies from the PH database here in the B through OIP column, you'll see that we get much larger errors on average and MAE. So basically our goal here was to try to bridge this gap. We're really, really happy with MOPAC and PM6 for the speed with which we can obtain these results. But we wanted to see if by reparameterizing the default PM6 parameters, we could kind of close the gap in terms of accuracy and potentially push the vibrational frequencies to even larger molecules. So to do that, we're just using the Levenberg-Marquardt algorithm to optimize the parameters, here denoted beta. And these aren't the full set of parameters for PM6. We've chosen somewhat of an arbitrary subset that made the optimization go quickly. And here we can actually feed in true anharmonic frequencies, where true means either experimental or computed using a high-level ab initio method. And then this gets back to using pbqff as a library, because each column of this Jacobian or gradient matrix can just be computed with a call to pbqff. So pbqff spits out anharmonic vibrational frequencies, and the columns here are the gradient of those vibrational frequencies with changes with respect to changes in the parameters. So we can call pbqff over and over to reparameterize PM6. And this is just showing briefly what Jonathan mentioned earlier, I guess the conventional way of including external parameters in MOPAC computation is to use the external keyword. And on the left, you can see just an example of a parameter file, as was mentioned, I think, in the previous talk. And my very minor contribution, with a lot of help from Jonathan, was that if you omit the keyword, you can actually include this kind of begin and end external block directly in your MOPAC input file without having to include a second file. So with that, I can move into my results. So this is actually basically the same table as we saw before, but this time there's an included column called PM6 opt. So this is applying our optimization algorithm to the results, or to the parameters, sorry. And you can see that we've gotten a lot closer to these best results. We've decreased the average deviation from them by down to 1.8 wave numbers, and the mean absolute error down to 11.6, with a maximum deviation of only 32.7 wave numbers. And this actually beats out B3LYP 4-31G that we saw before. We can see the same kind of behavior applied to other molecules, such as acetylene, where here we've gotten the error down to basically 0 in all three metrics. And again, we do somewhat similar on ethylene, but this time the max is quite a bit larger, and we barely beat B3LYP only in terms of the average. Now, the downside of all three of these cases is that this was training the parameters on a single molecule at a time. So this is very different from how PM6 is optimized initially on a large representative set of molecules. So we're having some issues that you can kind of see in this graph of potential overfitting and the parameters not transferring well to other molecules. So what I'm trying to show here is basically some quantitative as well as qualitative differences between the optimized parameters in each case. So for example, in this case, for ethylene, the optimized parameter FN11 is much larger than the default value, whereas for the other two molecules, it's below. So this is perhaps even better reflected in some of the summary statistics for benzene, where you can see that taking the parameters optimized on this molecule and applying them to benzene gives us statistics that are actually much worse than the scaled harmonic frequencies from B3LYP 4-31G. So to combat this, again, we think it's probably an issue of overfitting on the single molecule training sets, which seems kind of obvious. So now the project I'm working on is doing a multiple molecule training set, again, only on 5 molecules at a time. But we're hoping that because polycyclic aromatic hydrocarbons are such a kind of uniform set of molecules, uniform class, that we can try to use a small training set of chemically similar molecules to capture something about them in the parameters. So this work is currently underway. It's been basically derailed by our supercomputer being down for the past 4 months. But I do have some preliminary results here. And you can see that this is just a 2-molecule reparameterization on cyclopropanilidine and ethylene. And already the errors are much lower than we saw in the single cases, although we're still trailing B3LYP again. We also noticed that PM6, the default, actually performs quite well aside from the CH stretching region at around 3000. So if you combine our optimized values above 3000 with the default PM6, you get these data down here, which you can see are already much better. And we've also applied this to naphthalene, and I think by now we've even applied some of these parameters to molecules with like 3 and 4 rings. And we're seeing something similar where we're doing pretty well, still not as well as B3LYP, as well as we would like, but we're getting better. And of course, this probably doesn't even need to be shown here, but comparing the timings for these quartic force fields, if we look at the time it takes to run just the harmonic frequencies for the scaled values in B3LYP, those are very fast. But if you wanted to run a full quartic force field using B3LYP 4-31G, which we want to do because we want the explicit anharmonic frequencies, then it would take a very long time. I mean, over 14,000 CPU seconds just for ethylene. And whereas when we use PM6, the scaling is much, much lower. So in conclusion, reparameterized PM6 is pretty good. And it's really fast for these PAH computations and hopefully for infrared spectroscopy in general. And of course, we do need to extend the training set to avoid overfitting, which we're working on right now. And then on top of that, the code I'm using for these reparameterizations is actually also open source and available on GitHub. So we're hoping that we can apply this to other kind of uniform classes of molecules. So these are some aluminum nitrides that have some kind of environmental applications that someone else in my group is working on applying the code to. And with that, I'd just like to acknowledge my group. I just finished my PhD, so I guess my former group technically, as well as these funding agencies and Ole Miss and Jonathan for inviting me. So with that, I'll take any questions you have. Thank you.
Thank you, Brent. And yeah, I guess I should have introduced you as doctor then. I wasn't clear that you had graduated.
No, just a month ago. So
Okay, well, congratulations on that.
thank you.
So are there any questions for Brent? So I have a question to start. So I guess you're using, you just mentioned you're going to release it. You're using a custom parameter fitting code for this
Yes.
project. Did you consider trying to use the param code that comes with MOPAC? You may have started this project before MOPAC was fully open source, and param was not easily publicly available, so that maybe was not an option when this started. But as the project is ongoing, that may be something possibly to look into. That could, I don't think it's able to fit to vibrational frequencies directly, but it has a way of setting up linear combinations of energies from different structures, and you can use that as a finite difference approximation of a vibrational energy potentially to have something that fits that somewhat directly.
Okay, yeah, that's a great suggestion. Actually, yeah, I did start working on the code before the open source release, but yes, I should look into param. That's a good suggestion.
And if you have any difficulties with param, don't hesitate to contact me.
Okay.
Yeah, and the
thank
same
you.
here. I mean, we're trying to make these tools as widely usable as possible, and
Awesome.
especially there's not a lot of online documentation for param. There is some manual web pages, but they're not actually on the website. But they will hopefully be integrated into the new website during the migration.
Okay, awesome. That's good to know.
Great. Are there any other questions for Brent? If not, I guess we can go to our next speaker.